Okay, so let's talk about this idea of entropy in a little bit more detail. And again, this ties back into Gibbs free energy and spontaneity of reactions. But let's make sure you understand what this whole entropy idea is. So, a good example that kind of helps with understanding entropy is the idea of melting ice. So, will ice melt spontaneously? Do you have to do anything to get it to start melting if you put a piece of ice on a table in front of you? No. So yes, ice melts spontaneously. All right. The next question, think this one through. Is ice melting exothermic or endothermic? All right. Is the ice giving off heat or is the ice absorbing heat? Think about it. You've got your ice, which is a solid, which means those molecules are moving a little bit, and then it converts to liquid, where your molecules move more. The only way that happens is if you absorb energy. So it's endothermic. All right? So that means our delta H is going to be positive. This has to be an overall positive value and bigger than my delta H to get that negative free energy. All right, so that means we need our entropy to be positive. So entropy is defined as the tendency of a system to move towards maximum randomness. All right, so we use S for the symbol of entropy. Positive means an increase in randomness. Negative is a decrease in randomness. All right, so thinking about that ice and liquid water, which has more random molecules, less organized, moving around more. The liquid. All right, so when ice melts, the reason why we can get it to melt spontaneously is while it doesn't favor spontaneity because it's endothermic, the increase in entropy of going from solid to liquid outweighs that. So that's how we get the overall negative delta G. So, generally speaking, it's easy to increase randomness. Molecules and reactions just tend to go in that direction. It takes work and energy to put things back in order. All right, so an example of this is something like, consider leaves falling from a tree, or seeds or something like that, acorns. Do they fall into a nice, neat little pile when they fall off? No, they fall randomly all over the yard. And then you have to go out there, or maybe your lawn care people or whoever, but you've got to go out there and rake them up, use a leaf blower, something like that, and put them into a pile and get rid of them. All right? This takes effort. The leaves falling off the tree didn't. They just fall. All right, so randomness is something that's kind of easy to increase. To decrease randomness takes effort. So let's think about this. What do you think happens to entropy when ammonia gas reacts with hydrogen chloride gas to make solid ammonium chloride? All right, so we're taking two gases and forcing them to become a solid. So our delta S in this case is going to be negative. We're going from randomly moving gases to nice, neat, situated solids. All right? So another way to kind of think about this sort of idea is, let's say then we know that this reaction is spontaneous, which means we need to get a negative delta G. All right, we're going to put in a negative delta S value here. All right, so if you subtract a negative, that means you're adding the entropy value. How do I get delta G to be negative? What does my delta H have to be? All right, so my entropy, and when I plug it in, when I multiply it by its temperature and then subtract that negative value, subtracting a negative gives you a positive. So the only way for me to get an overall negative value is if I have a large negative delta H. So that's kind of the thought process that some of these questions are going to take you through. All right? So just some things to remember. There's a lot of signs related to stuff here. So, negative delta H is exothermic, positive delta H is endothermic, negative delta G is spontaneous, positive delta G is non-spontaneous, positive entropy, or S, increases randomness, negative S decreases randomness. All right, those are things you want to make sure you keep straight.